All right, so we're going to go ahead and finish up chapter 2, section 3, techniques for computing limits continued. And the best way to show you what's going on is actually going to be some examples. So the first thing we're going to do is start with some examples. For our first example, we're interested in evaluating the limit as x approaches 2 of x squared minus 6x plus 8 divided by x squared minus 4. Now I've drawn the graph below, and it's pretty easy to see that we can't find the limit by just substituting in a, right? We get a divide by 0 error for our bottom function. So even though we've got two polynomials, we've run into a problem. So what can we do? And one of the things we can do is factor out what our numerator and our denominator look like and cancel some terms. So you're probably saying, Emily, what does that mean? And I'll go ahead and show you. So let's consider our original limit, x approaches 2, x squared minus 6x plus 8 over x squared minus 4. And that's going to be the same as the limit as x approaches 2 of the numerator factored, which becomes x minus 2 times x minus 4 over the denominator factored, which is x minus 2 divided by x plus 2. And here it's easy to see that we can just go ahead and cancel out x divided by 2 because we have one copy in the numerator and we have one copy in the denominator. Now our limit is a lot easier to manage with because we don't have a divide by 0 error. Now we've got the limit as x approaches 2 of x minus 4 divided by x plus 2. Now we can go ahead and do exactly what we wanted to do and just directly substitute in 2. We get 2 minus 4 over 2 plus 2 equals negative 2 over 4 is the same as negative 1/2. So though it may seem a little daunting, the first step you should always try is asking yourself, can I factor the numerator? Can I factor the denominator and get anything to cancel out? Now let's move on to our second example. And this one is going to be a little bit more involved, but that's definitely okay. We can definitely do that sort of thing. I believe in us. And it's going to involve using the complex conjugate of numbers. So we're interested in finding the limit as x approaches 1 of the square root of x minus 1 divided by x minus 1. And here we've got a numerator and denominator that both go to 0 when we plug in 1. So we definitely can't just directly substitute in a here. We're going to have to do something else. And because neither of these is a polynomial we recognize, we can't just factor the numerator and factor the denominator. So I would like to say that the square root of x minus 1 divided by x minus 1 times the number 1 is equal to the square root of x minus 1 divided by x minus 1. Now this 1, well, we could just use the number 1, or we could use the conjugate of square root of x minus 1, which would be square root of x plus 1 divided by square root of x plus 1 instead. So if you'll agree with me, I've got something that's the exact same in the numerator as it is in the denominator, so we can divide those out together and we just get the value 1. So it's totally fair game for me to go ahead and place this right here where I have 1 written. So I'm going to go ahead and do that. And I get square root of x minus 1 times square root of x plus 1 all over x minus 1 times the square root of x plus 1. I'm going to expand the numerator. And when I do that, I get x plus the square root of x minus the square root of x minus 1. I'm going to leave my denominator alone. That's a pro tip for you right there. And now I see that these two central terms are going to cancel out. Those cancel out, and I'm left with x minus 1 on top divided by x minus 1 times root x plus 1 in my denominator. And wham, bam, thank you, ma'am. We get something on the top that's the same as something on the bottom. We can go ahead and cancel those out. We say that these are the same as 1 divided by square root of x plus 1. And that's how we get from something that we can't figure out to something we can figure out. And here it's pretty easy. We can just go ahead and directly substitute our value for a. So let's go ahead and substitute in a. We get 1 plus the square root of 1 plus 1, which is the same as 1 over 1 plus 1, which is the same as 1 over 2. So it took a little finagling and it took a little mastery of some algebraic steps, but we were definitely able to figure out the limit as x approaches 1 of root x minus 1 divided by x minus 1. So finally, I want to show you something that's probably a little bit more difficult. And in this case, we're interested in finding the limit as x approaches 2 from the left, x approaches 2 from the right, and what the value of our limit as x approaches 2 is for our function f of x. And in this case, f of x is equal to x cubed minus 6x squared plus 8x divided by the square root of x minus 2. So we know that anytime we get a 0 in our denominator, we can only have a domain where x minus 2 is greater than 0. So x has to be greater than 0. Sorry, x must be greater than 2. So automatically we know that we can't approach we can't approach 2 from the left-hand side because all of our values of this have to be greater than 2. So we can't approach 2 from the left. And what does that mean for us? It means that the limit of f of x as x approaches 2 from the left does not exist at all. And we know from our theorem 2.4, the limit on the right has to equal the limit on the left in order to have the limit exist at all, that if we don't even have a limit on the left, then we don't have a limit at all. So this means that the limit as x approaches 2 of f of x does not exist. And so that leads to the question, can we even calculate the limit as x approaches 2 from the right? And the answer is yes. Yes, we can. We certainly can. We're just going to have to be clever about it. And this time, we're going to do the same trick that we did last time. We're going to start by factoring our numerator, and we're going to rewrite our denominator so that we don't have the square root sign, but instead we have it to a fractional power. I ran out of room, so we're going to the side instead of down. So we're interested in the limit as x approaches 2 from the right of a function f of x, which is the same as the limit x approaches 2 from the right of x. And here you see I've factored my numerator into x times x minus 2 times x minus 4, all divided by x minus 2 to the power 1/2. And I can do this because square root of x minus 2 is the same as x minus 2 to the power 1/2. So I'm going to go ahead and take that step. Well, I've got one copy of x minus 2 in the numerator, and I've got a copy in the denominator raised to the power 1/2. Well, the copy in the numerator is actually x minus 2 to the power 1, and the copy in the denominator is x minus 2 to the power 1/2. We know from algebra that in order to cancel these out, we take the power in the numerator and subtract the power in the denominator, and we're left with the limit as x approaches 2 from the right of x times x minus 2 to the power 1/2, because we have 1/2 left over, x minus 4. We can use our limit laws here, and we get the limit as x approaches 2 from the right of x times the limit as x approaches 2 from the right of x minus 2 to the 1/2 times the limit as x approaches 2 from the right of x minus 4 all together. So now we can just go ahead and plug it in. We get 2 times 0 times negative 2. Well, anything times 0 is 0, so our answer is 0. And that's it for this section. Next, we're going to go on to a quick theorem. So this theorem that I'm going to talk about is pretty important, and you could tell it's important because it has its own name. It's called the squeeze theorem. And what the squeeze theorem tells us is that sometimes it's not very easy to calculate a limit, right? You saw that we had to do all sorts of tricks and tips and hints because we didn't know what was going on when we had a hole in our graph. So the squeeze theorem is here to help us with that. So assume that the functions f, g, and h satisfy f of x is always less than or equal to g of x, is always less than or equal to h of x for all values of x near a, except possibly at a. A doesn't have to be defined. But if the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, and they all equal L, then the limit as x approaches a of g of x is equal to L. And you're probably wondering, well, Emily, what does this look like? And the answer is coming in the form of a few more examples. So what I've got going on right here is definitely a very busy screen, but we'll certainly break it down. So let's start with what's going on with this black curve here. So I've highlighted it, and I'm going to call this one g of x. And this is the graph of x squared times sine of 1 over x. And in this case, we're interested in what happens as we approach 0. And we can see if we zoom in, what's going on at 0 is we just have a lot of oscillations. It's super busy. We don't really know what's going on there. So we can't exactly plug in 0 and get anything meaningful. Instead, we're going to use the squeeze theorem. And this says that if I've got a function on top and a function on bottom, and my black function is in between those two, and my function on top and my function on bottom both have the same limit where I'm looking, then my middle function is going to have that limit. So as I approach 0, h of x goes to the value 0. So the limit as x approaches 0 of h of x is equal to 0. And now I want to ask questions. Let's build the graph of f of x equals negative x squared. And I want to say, well, what's going on here at 0? The limit as x approaches 0 of f of x is equal to 0. And we know this because we can just plug in 0 because we've got polynomials, right? So the squeeze theorem tells me, well, f of x is always less than g of x. G of x is always less than h of x, and I've got the limit as x approaches 0 of f of x is equal to the limit as x approaches 0 of h of x. So the limit as x approaches 0 of g of x must also equal 0 by the squeeze theorem. And this is probably very bizarre, and you're thinking to yourself, well, Emily, this is a very hard function to find a 0 of, and you just plugged it in and got out the answer, right? Well, let's do a few examples and see what we can't come up with. So the first example is this one. We want to use the squeeze theorem to find the following limits. And the, oh, sorry, oopsie. Okay, we're good. We're doing good. I just keep turning off my screen. So the first function we have is actually sine of x. And I want to build a function on top that's always positive compared to sine of x. And for this one, I'm going to choose the absolute value of x. And why do I choose that one? Because it looks a little something like this. And if I choose the absolute value of x, then maybe I want to choose the negative absolute value of x. So we can clearly see that sine of x is always going to fall in between these two when we're between negative pi over 2 to pi over 2. So they're going to have the same limit. And that limit is going to equal 0. The next thing that I might be concerned with is cosine. So for cosine, well, why don't I make my life easy? And I'll pick something that looks like the negative absolute value of x in the form of 1 minus the absolute value of x. And then for my h of x, I just want the straight line x equals 1. And clearly, we can find the limit as we approach 0. So as long as you know what these functions look like, and as long as you can visualize building a function in between, we can squeeze or sandwich our function in between two built functions. And that's exactly what we want to do. So that's this video. I hope you understand. If you've got any questions, feel free to email me, and that'll be it for today.